So we're going to continue on talking about cache coherence. Um, First, let's just quickly review what do we mean by coherence. We say a multiprocessor is coherent if the results of any execution of a program can be reconstructed by a hypothetical serial order. So it means several things. One is the so-called write propagation. Write propagation means that any writes should be made visible to all other processes and processors. The other important aspect is the write serialization. You may have many read and write operations on one memory location or data. We require that all writes to the same location are seen in the same order by all processes. And also we mean that all the locations called these same order to all the locations called write atomicity. So here's an example. If a write 1 followed by write 2 seen by a read from processor 1, and this should be the same order by all the other reads by other processors. So, we're talking about a multi-core environment or multi-processor environment. If one processor sees W1 is followed by W2, W1 means the first write, and W2 means the second write. If we see this order in processor 1, and we require that's the same order seen by all other processors. If that's the case, it is so-called coherent. It's not that easy if you talk about multi-core processor or multiprocessor environment. We have one example here. The black box, in fact, is P1. We see two variables, A0 and B0, and these two variables are in a shared memory environment. And we have these four processors. They are connected in series. So P1 connects to P0. Sorry, P0 connects to P1, and then to P2, and then to P3. And these are connected in series, which implies that the propagation of messages are going to go through this sequence in order. So any message that goes from P0 to P3 has to go to first P1, then P2, and then P3. Let's assume that at time 0, T1, at time T1, processor 0 updates the value of A. So it writes 1 to the variable A, and that overrides the initial value of 0 on P0. Also, in the same time slot, P3 updates the variable B, so it writes a new value 2, and that is going to overwrite the old value of 0. However, these other operations happen on these two separate processors. If we propagate these write operations on this path between P0 to P3 or between P3 to P0, we see this is how they're going to be propagated. So in a time T2, this new value of A is going to be seen by processor 1, and then at the same time this new value of B is going to be seen by processor 2. So at some point after T2, what will happen is this new value of B is propagated to P1, and similarly the new value of A is propagated to P2. And following that, the next time slot, the new value of B2 is propagated to P0, and new value of A is propagated to P3. So from looking at this timing diagram, you can observe that on these two processors, since it's closer to P3, which updates the value of B, so these two processors will see B's update before seeing A's update. And similarly, these two processors will see A's update before seeing B's update. So the order of these updates, the order of these writes are different perceivably by these two processors, these four processors. So this is incoherent. This is not the coherence we want to achieve. In the next few slides, we're going to talk about bus-based coherence protocols. Here we assume all the processors are connected to a bus, and all the processors use write-through cache. So all the writes will be shown as a transaction on the shared bus to memory. We're going to talk about two protocols, update-based protocol and invalidation-based protocol. This is the write-through cache with update-based protocol. In this example, we have three processors, each has its own private cache, and they are connected to a bus, and also the shared memory is connected to the same bus. In this bus snooping protocol, the cache controller of each processor, which is somewhere here, 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 and each cache of these processors has a cache controller, which can constantly snoop the bus. So it knows what's the read and write transactions that are happening on the bus, the address, and the value. And these controllers will, depending on what kind of transactions seen on the bus, it will probably update local copies of its own cache. So in this here, we assume this the current value we have. We have in the memory the value of x at this location is minus 100, and this processor has this value in its own cache, and then the other processor has a new value. This value, because of the write to this local copy, and this write operation will generate bus transaction. Because it's read through cache, so this processor will write the new value to the memory, and also the other controllers of these caches will see this write operation. It knows that this is a write operation to address x or variable x. It knows that it has a local copy of x, and then it will update its local copy. So that's why this is called update-based protocol. The next transaction you'll see is the value in this local cache is updated to the new value. Now, a different mechanism can be implemented. Still using write-through cache, we can use invalidation-based protocol. So assume the same situation that this processor P here writes the new value x. Okay. Because it's write through, so it's going to update the content in memory. And also this transaction on bus is seen by the cache controller of this first processor. What it will do here is, instead of updating the content of the copy in this cache, it will invalidate this copy. So that copy is gone. Okay. Now, consider this case. This processor load the value again. In this case, what will happen is this will cause a cache miss. And this cache miss will cause a load operation to load the value from memory. So as a result, once load completes, it will have a local copy in its cache. So we use state machines to describe these coherence protocols. And in the following example, this is a very simple Snoopy coherence protocol for a write-through cache, no read allocate. So if it is a write, if there's a miss, it will not allocate a cache line. That's the meaning of no write allocate. So we maintain the state of the cache lines is either valid or invalid. And with this solid line, this arrow, what we're saying here is if there's a processor read operation, we will of course cause a cache miss, so it will load the updated value from memory. That's why it's going to generate a bus read transaction on the bus. And once the memory supplies the data, it will change the state of the cache line to valid. If there's another processor read, since we already have a local copy, so there's a cache hit, so it's going to stay valid. And if it's a write operation, okay, that means I'm updating my local copy, so the copy I have is still a valid copy, and it will generate a bus write protocol. And this bus write protocol, transaction, will be seen by other cache controllers, and the other cache controllers will update its local copy. And in fact, it's doing this. If any other cache controllers sees a bus write, it will invalidate its local copy, because the reason it stays at here is the other processor has a local copy, and because of the recent processor write, that local copy becomes out of date, so it will change the state from valid to invalid. And this bus write is because of this bus write transaction generated by the processor read. Processor write. For this case, if it's invalid, that means I don't have that local copy. And if there's a processor write, because we're doing no write allocate, so we will not allocate a cache line. So this write, this new value, will go through directly to the memory, because it's a write through. And also this operation will generate a bus write transaction, which will also cause bus write seen by other cache controllers. Now, what about writeback cache? Writeback cache is designed to reduce bandwidth requirement, so we do not have to every time write to the main memory if there's an update to the local copy. We only update to the main memory if that updated cache line is evicted out of the cache. So with writeback cache, the majority of local writes are hidden behind the processor node. Okay? So we will not be able to detect the most recent update to the copy if you're using writeback cache, because it's not going up to the bus. So how do we snoop, and how do we maintain the right ordering? we add a new state, or if a cache is the only one that having a valid copy, and memory may or may not have it, we consider that cache has an exclusive copy of a line. A line means a cache line. So we say it's a modified or dirty cache line when the cache line is the owner of the line. When it's the owner of the line, it must supply the block because it has the most recent value. So let's look at this example. This is the cache coherent protocol. We're using Writeback cache, and this is update based. Let's assume that we have all these three processors have a local copy of X, and the most recent value is -100, so it has all these cache lines have -100, and this is consistent, coherent at this point. All the processor nodes share the same data. Now let's say this processor P generates a write operation to cache line X. Okay, so this new value X, has to be seen or propagated to all the other cache blocks through the update. This is how the system can ensure the cache coherent. Okay. But next time, when the first processor is going to load the value X, there will be a cache hit. Let's assume that the second processor writes to the cache line. This write operation should be updated to all other caches that have the local copy. So that was the update based. Here we show you the invalidation based. So if there's a write operation, we're going to invalidate all the other caches that have the local copy. If it's a load, there will be a cache miss, and the controllers will generate this request. Because the third processor has the most recent update value, it's a snoop hit. So the controller knows that it needs to supply the most recent value to the cache. They're requesting this value. And next time when it stores, because this is a update operation, write to the value, so the controller will generate a invalidation message to invalidate the other copies in the caches. And you can see that the process can keep doing this store operation without generating traffic. So from those two state shared, valid, invalid state machine, now we have a new state machine. We call it MSI. Yes.
So in this write-back scheme, the cache coherence protocol, so the data will never be updated to the memory. No, if you go to the other slide.
Yeah.
So it's always among the processes. So the memory is never updated.
Right, because this is write-back cache. So if the cache block was evicted, that's when the new value will be sent to the main memory. So if you load another memory block, which will take the same location of the, you do cache replacement. So that's what I mean by evicting. Yeah. So we have this MSI write-back invalidation protocol. We have a modified state, which means that the cache line is dirty and only this cache has a valid copy. So that's the case we saw in the previous slide. One processor keep updating its local copy, so all the other processors' cache will not have a copy of that cache line. Second state is shared. The memory is consistent. Everybody has the same value, and one or more caches have a valid copy. And the third state is an invalid state. We're using write-back protocol, which means a cache line can be written multiple times before the memory is updated. To illustrate this protocol, we assume that there are two types of requests from the processor read and processor write. And we have three types of bus transactions posted by cache controller. Bus read. Bus read is generated because processor read has a miss in the cache. In this case, either memory or another cache will supply the line. The second transaction is so-called bus read exclusive. Bus read exclusive is to read to own. Okay, to have that cache line exclusively. And this is generated when processor write is issued to a line which is not in a modified state. And the third type of bus transaction is bus write back, and this due to replacement. So we have these three states. In the very beginning, a cache line is at the invalid state. A processor read operation will cause a cache miss, so it will generate the bus read transaction on the bus to load data. Once the loading is completed, it will change the state of the cache line from invalid to shared. So it has a copy which could be shared by other processors. And after that, if read operation continues, it will stay at this shared state, and there will be no more transactions generated on the bus. If it is a modified state, that means the cache line is written by this processor. That's when it's at modified state. If it is at that state, a read operation following that will keep itself remaining at that state. To get to this modified state, you can either go from this invalid, and in this case, if a processor write to a cache line that's invalid, it will generate a bus read exclusive, basically to own that cache line. And after that's completed, it will change the state from invalid to modified. The other possibility is to change from shared state to the modified state. And still, it's due to the processor write. Because when I'm writing to my own copy, even though it's shared, after I write, my copy is the latest copy, and all the other copies in other processors' cache should be made invalid because they are out of date. So in this case, it will generate bus read exclusive. And to complete this, for processor write, it's modified, it's going to remain at modified without generating bus transactions. So this is what we see from the processor request. Okay. This is a controller should do. Basically, we're talking about the processor's own controller, because these are the processor's transactions. So if I'm the cache controller, I'm going to look at the transactions coming from the processor, and then I'm going to do the state transition based on this state transition diagram, state machine. Now in this slide, we're going to look at bus transaction. This is from point that if I'm the cache controller, I'm looking at the bus. I'm snooping the bus to see what kind of transactions that's happening on the bus right now. And as you know, these transactions are due to other cache controllers. The simplest is the shared state. If my cache line is in the shared state, that means I have a valid copy. And if I see a bus read, that's because someone just read the data and it doesn't have a copy. So on the other processor, there's a cache miss. So that's why a bus read is generated. So if that's the case, I'm going to stay in shared state. From modified, if my cache line is currently a modified state, and if I see a bus read, that means some other processor is trying to read the same cache line, and because I have the cache line in the modified state, that means I have the most recent copy. So I will flush. That means flush the data on the bus. So the other cache controller that requesting the data will be able to receive the data. In this case, when flush happens, both the memory and the requester will grab the copy. That's the most recent copy. if I see a bus read exclusive, the reason we see this is because some other processors just write to that cache line. So my copy becomes out of date, so I will invalidate my copy. And similarly, we will change our state from modified to invalid if we see a bus read exclusive, and then we're going to flush the cache line. Another possible implementation is doing this. Instead of changing my state from modified to shared, I will change from modified to invalid, just basically invalidate my copy when I see a bus read operation. In that case, my value is propagated to the main memory. And we do this, we think that there will be no more reads from this processor. We're going to save later invalidation trip. Because if you change this shared, and if there's a bus read exclusive, you're going to again change the state from shared to invalid. So you're going to have the same effect. So that's why we have the second option is to just change from modified to invalid immediately. So this is the overall state machine. We basically write these we combine these two state transition diagrams into one. Some of them are processor initiated, some are bus snooper initiated. So we're going to have this example here. Let's assume that we have these three processors, each has its own private cache, and these caches are connected to the bus, which in turn connects to the main memory. And in the main memory, we have the initial value of location X, 10 here. Let's see what's going to happen when we see a processor 1 read X. If you look at time in the state transition diagram, we can try to figure out because there's no valid copy in processor 1's cache. So that means the initial state is invalid. We have a processor read. So what should be my next state? So if we follow that, it's going to be a shared, right? Also, we're going to generate a bus read. A bus read transaction on the bus. Bus read transaction because none of the other caches have the copy, right? So the cache controllers of the other two caches will not do anything on this bus read transaction. So it will what? The bus read will cause the loading of data from memory to process 1's cache. So we updated the cache line. We have the value 10 loaded from memory, and then we mark the state of the cache line as shared. So this is what we will see when this bus read happens. So the state in P1 is S, and state in other processors are invalid, and its memory supplies the data. Okay. Now let's see the next action from the processor. P3 reads X. So P3, because its own state is invalid, so P3 will follow this path, right? Invalid to shared state transition. It will also generate a bus read. Bus read. What's going to happen next? P3 will get the data and put the cache line into shared state. Who supplies the data? Okay, let's see if P1 will supply the data or not. Okay, at this point, P3, the cache controller of P3, generate this bus read request, right? So this bus read will be able to reach every other cache controllers. So every other cache controller will see this bus read. P1 has its cache line in the shared state. So that's here. The shared state, when it sees a bus read, what does it do? According to this state transition diagram, it doesn't do anything, right? It just keeps its own state. So it will not supply data, in fact, the way we designed this protocol. So it's still the memory supplies data. So after this action finishes, we're going to have this cache line in shared state in P3, and that was the bus transaction generated, and it was the memory who supplied the data. Next transaction, the animation here is some problem, but what we're trying to see here is P3 writes X. P3 writes X because P3 is shared state. When does processor write? It's during this transition, right? So it's gonna translate the state from shared to modified. Also, it will generate a bus read exclusive. This is a bus read exclusive generated on the bus. by P3. So for P3, we know that the state will be changed from shared to modified. And let's look at what's going to happen on P1. P1 will see this bus read exclusive. Right? And because P1 is a shared state, so it will do what? It will transit state from shared to invalid because of the bus read exclusive. And that's it. It does not do anything else. So that's why we see an invalid state in P1, a modified state in P3, and the person who supplies data is memory. Okay, that's invalidate the cache line in P1. The previous slide, okay. Here?
Yeah.
This one?
No, the last one.
Okay, this one? Okay. Does not come from memory if having bus upgrade. I think what this means is that we'll see for some other processors, if they want to later load location X, load variable X, it's gonna be supplied by P3 rather than the main memory. I think that's what's going to show here. In this case, let's say P1 reads X. P1 reads X. We know P1 is now at invalid state, so processor read will generate a bus read transaction. So we'll see a bus read transaction show up here. And then this bus read transaction will be seen by P3, which has the cache line in modified state. Right? So which state P1 should change to? P1 will go from modified to shared state. P3 will go from modified to shared state. Also, it's going to flush data. Flush data on the bus. And P1 is the requester. So P1 will get the data because of that flush. So this is the flush because P1 is requesting the data to get the copy. Also, the data is put into the main memory because of the flush. And we're going to update both of the states as shared. Okay, next operation, P2 reads X. P2 reads X. P2 has an invalid state. It's a processor read, so it will generate bus read. So it will change to shared state. And the other two processors, both of them are in shared state. When they see a bus read, they will remain at remain at shared state and generate no other bus transactions. So who supplies the data? Because we don't see a flush here, so it must be the main memory who supplies the data. Okay, we described the MSI Writeback Invalidation Protocol. There's an enhancement protocol based on that. It's so-called MESI Writeback Invalidation Protocol. The idea is to reduce two types of unnecessary bus transaction. First, bus read exclusive, that snoops and converts the block from the shared to modified when you are the solo owner of the block. The second type of non-necessary bus transaction is the bus read that gets the line in shared state when there's no sharers. Okay. Both of them are dealing with the case that you are only owner and user of the cache line. And that's why we introduce this exclusive state. This is a state that a process can write to the local copy without generating a bus read exclusive. This is proposed by Pomakros and Patel in 1984. It's codenamed Illinois Protocol, and it has been used in Intel PowerPC and MIPS processors. So compared to the MSI, this MESI has one more state, the exclusive state. From the invalid state, if we see a processor read, we will either go to exclusive state if no other caches share the copy, or we'll go to shared state if there's indeed other caches share the copy. So that's the difference. If there's no sharing, we're going to go to this exclusive. If there is sharing, we're going to go to the shared state. In both of these two cases will cause a bus read transaction generated. If there's a write operation to this block, and this is the same as before, it will generate read is exclusive, and the state will be changed to modified state. From exclusive, if there's a read request, it's going to stay at exclusive. If it's a write, it will go to modified. When it's at modified state, a local reader writer will keep itself at modified state. For shared state, it will stay at shared state if it's a local read. It will become a modified if it's a processor write. Also, it will generate bus read exclusively. This is the processor request. Also, it has the bus transaction state machines. For modified, it will become a shared if there's a bus read. It will flush the data if there's a bus read exclusive. This is same as MSI. If it's a bus read, it will flush. It essentially becomes the supplier of the data. So this is different from the MSI in that in MSI, when there's a bus read, you don't do anything, but here it's going to supply the data. This is the so-called the bus upgrade. So it's going to supply the data if it's even if it's in shared state. And when there's multiple suppliers, there will be some selection algorithms to decide which one supplied the data. If it is bus exclusive from shared, it will transit to invalid, and it will flush data. It will migrate from exclusive to shared if it's a bus read. You can do either flush or not flush. And finally, this exclusive will become invalid if there's a bus read exclusive. And this is the combination of this processor transaction and the bus transaction. We can even add one additional state. It's called owner state. And with that, we got a new protocol, MOESI protocol. The old state processor will be responsible for supplying the data. It's the owner of the data. And this protocol has been utilized in Sun UltraSpark machine and AMD Opteron machine. So far, we talked about processors with one level of cache. There are some implications on multi-level caches because only the last level cache is connected to the bus. All the other caches that are closer to processor are not visible to the bus. So how do we guarantee coherence in a multi-level cache hierarchy? One option is to snoop all cache levels, and obviously that's a lot of complexity and overhead. Intel has some innovations in their chipset 8870. It has a snoop filter for quad-core machines, which can intelligently snoop transactions at multi-level caches. When we design multi-level caches, we often maintain inclusive property, which is to ensure data in the outer level must be present in the inner level. And that's true for all the modern processors that we use. So we only need to snoop the outermost level. For example, if we have 2-level cache, we only need to snoop the level 2. But level 2 also needs to have knowledge of the level 1 cache miss or hits. Level 2 needs to know level 1 has write hits. We can use a write-through cache, so whenever there's a write to level 1 cache, it will be populated to level 2. We can also do write back, but that requires another bit in the level 2 to indicate cache line was modified. In level 1, it's not being updated in level 2 yet. However, this inclusion property is not easy to implement. There's many challenges. For example, the replacement. Different buses observe different access activities. For example, layer 2 may replace a line frequently accessed in level 1, especially when level 2 cache is shared by instruction cache and data cache. So you may replace a cache line that's frequently accessed by level 1 cache. And split level 1 caches. That split means that you have separate instruction and data caches. In some cases, different cache line sizes. So level 1, level 2 may have different cache block size. You may or may not. So for example, if a cache level 1 cache has a 32 bytes cache line, level 2 have 64 bytes. So that means whenever you replace a level 2 cache line, you may end up replacing 2 level 1 cache lines. And one of them may not be needed to replace because it's still valid, has the valid data. So we can choose specific cache configuration. For example, we can use the same cache line size. We use direct mapping level 1, also direct mapping level 2, or set associative in level 2. The other option is to explicitly propagate level 2 actions to level 1. When we replace level 2 cache line, we will flush the corresponding level 1 cache. And whenever we see a bus read exclusive at level 2 cache, we will propagate that to the corresponding level 1 line by invalidating the copy. And to avoid excessive traffic, we can maintain some status, for example, the inclusion bit, to filter whether we need to invalidate cache line in level 1 or not. So let's move on to different interconnection of the molecular processors. In this and following slides, we're talking about processors are connected through some kind of interconnection network rather than a bus. In a bus type of connection, the processor's transactions on the bus can be seen by all other processors, by all other cache controllers. But in these interconnection network, for example, crossbar, these are different. The nature of this interconnection is to provide multiple pair of point-to-point communication. For example, this processor can talk to this processor. At the same time, this processor can talk to this processor, as long as they are using different ports. In this type of architecture, you cannot do snooping because the activities coming out of one cache controller cannot be easily seen by all other controllers. People use this type of interconnection is for scalability purpose, because in a bus type of connection, you cannot increase the number of processors connected to the bus to a large number. Whereas this interconnection network, you can essentially increase the number of processors connected more easily. So with this type of interconnection, how do we achieve the coherence? The idea is to use so-called directory-based coherence protocol. This is what we call directory. So it's essentially another hardware table that maintains the information of the data copies in the caches. This directory-based control shows that which processor has what copies. And of course, we need to use actual hardware to store this information. Essentially, we're going to keep each cache line a row. Okay, so this one row corresponds to one cache line. Okay. And this each column here in this row, this corresponding to the number of processors. This essentially records which processors have that cache line. So that's why the total number of bits or table structure you need to use is proportionally to the number of lines multiplied with the number of processors. Let's look at more closely this example. So we have these many processors connected to this interconnection network, and we have a shared memory. And in this directory, each line represents a cache line, the status of a cache line. And we represent the cache line as CK. The first bit here usually is a flag that indicates whether a cache line or cache block is modified or not. This 0 means it's not modified. And when we look at this line, we see some bits are 0, some bits are 1s. And these bits, each one of these bits corresponds to one processor. And in fact, the caches of one processor. So this first line is to say cache line CK has not been modified, and processor 0 and this processor K plus 1 have copy of this cache line. Okay, that's the meaning of these 1 in the line in this directory table. The second line here, second row here, the first bit is a 1. That's an indication that cache line CK plus 1 has been modified. And because of that, only one of the processor's cache can have that copy. And it is this second processor that has the copy. That's the meaning of this 1 bit here. So In summary, that we use this directory, the first bit, as the modified flag to indicate whether the cache block or cache line has been modified or not. And each of the following bits is a presence bit for each processor and each block in the memory. So this is corresponding to this first processor has the copy, and these second and first to the last processor have the copy. And this processor has a modified copy of cache line CK+1. And so on. Now, you may figure that we're going to use a lot of bits to store the presence status of each of the cache lines in all the processors. Okay? If you have n processors, you're going to have n bits to record the presence of a cache line. There's only one row. One variant of this cache-based, directory-based coherence protocol is to use limited directory. By limited directory, we mean that instead of using one bit for every processor to record the presence, we only allow a limited number of processors to have the copy. In this case, in this particular example, we in fact say that each cache line can only reside in 2 processors. How do I know 2 processors? We have total 16 processors in this multi-core processor. Each row here corresponds to a cache line. That's the same as before. The first bit is the modified bit. That's the same as before. Now the following bits. 1 here means it's present in one of the processors. Now which processor? We use these 4-bit encoding to represent one of the 16 processors. So by using this 1, 0, 0, 0, 0, we intend to say processor 0 has a copy. The next 5 bits, we see another 1, and we see 1110. That's processor 14. So using these next 5 bits, we intend to say processor 14 has a copy. So that's what these arrows are indicating. In the second row, we have modified bit set to 1, so that cache block has been modified. And we know that only one of the processors should have the copy. And which one? The presence bit and then 0001. That means processor 1 has that copy. The next 5 bits start with a 0. That's an indication of no other processors have the copy. So that's a null pointer, null indicator. So using these 10 bits, okay, we can record the presence of the cache line in 2 out of these 16 processors. compared to the full directory, we would have to use 16 bits to store that information. And of course, the benefit is you can allow many processors to have the copy, where in this case, we only have 2 processors that may have the copy. In the previous case, we saw that the memory is illustrated as a one big module connected to the interconnection network. A different approach is to distribute these memory modules, because centralized memory and centralized directory is less scalable. In this case, we have processor, local cache, and then it has a local memory. And that's the same for every other processor when the cache and memory units. Still, even though these memories are distributed, we use them as a shared memory. That's why it's called a distributed shared memory. This is mainly for scalability purpose. One unique feature of this organization is that when the processor accesses data from memory, it incurs 2 different speeds. If the processor requests data from its local memory, it's much faster than it requests data from a remote memory. By remote, we mean the memory attached to a different processor module. So that's the term called non-uniform memory access, or NUMA. And if we have coherent cache and memory hierarchy, we call this type of architecture as CC NUMA, cache coherent non-uniform memory access. So compared to the centralized shared memory and the centralized shared directory, we can distribute these directories just like we distributed memory for the benefit of scalability. A variant of this distributed shared memory is Stanford Dash, where as CPUs organized in clusters. For example, this one cluster has 4 CPUs, each has its own cache and local memory. They are connected to a bus, so you can still do snooping protocol here. But these clusters can be connected through an interconnection network to scale up in terms of number of processors and size of memory. And on this interconnection network, we use this distributed directory to keep the status of these shared cache lines. And directory keeps one of the 3 status: uncached, shared, or dirty. So the memory hierarchy has several levels. The processor level, okay, and across processors, you can also do cache-to-cache transfer. That's called local cluster level. And then you can do home cluster level. If the block is dirty, that means one other processors have the most recent data. In that case, it needs to get the most recent data from a remote node which owns it. And in that case, it's called remote cluster level. So let's look at this example. We have this distributed shared memory, and we also have this distributed directory. We have a variable z, which resides here as its home. So this processor is the home of z, and it is in shared state. And this 1 indicates that this processor and this processor, the home, has valid copy of this data z. That's the directory. So currently data z is shared. It's clean. If this first processor wants to read z because it does not have a local copy, it will generate cache miss. And because it does not have that cache line record here, so it will need to go to its home node. Now the question is, how do we know which one is its home? It's normally calculated based on the address. So you have the whole address space. If you have 16 processors, for example, then you divide the whole address space into 16. Then based on the address, you know where it's home. So that's what I'm trying to explain. The way to determine the home node is typically by using the address. Because when you load variable z, you're using the address, right? You load, the loading instruction is the address. So if the whole memory space is partitioned into 16 chunks, let's assume you have 16 processors. Then let's see the particular address you want to load falling to which one of these 16 chunks. Then that node is the home node. So the home node is unique, no matter which processor loads what address. So in that case, this processor will go to the home node, where it finds that this data z is in shared state and two processors have the copy. And as a home node, the processor will supply the data from its own memory. So it will be updated to the cache of the requester. And then the directory will be updated. Now in a different example, let's assume that data z is dirty. So in the directory here, we mark this as a modified, and also we record the processor who has the most recent value. That's this processor. So in this case, because this is dirty and this processor has it, so no one else has the most recent value. If the first processor does a read again, it will ask for information about data z. It will query the directory of the home node. It knows that that cache line has been modified and this processor has the most recent value. So it will send a request after the directory responds with owner information. This requester will send a data request to the current owner of the data, the most recent value, and then the owner will do two things. It will update the value of the requester. It will also update the home node by sending the most recent value. And after that, it will clear the flag. Because now everybody has the same value, especially the home node has the most recent value, so it's not dirty anymore. So finally, the state of the data Z is clean and it's shared by 3 nodes. Another example. Let's assume that these two processors have the shared value. Z shared. Both of these processors have a copy of its own cache and also in the home node's memory. That's what's indicating in this directory entry. If we write, we see a write miss. I'm going to go to home node. Okay. When it goes to home node, the directory controller will respond with the information about who has copies. So it will respond with sharer's information. It will supply the data. This requester, who writes it last, will then send invalidation signal to invalidate the directory. Invalidate the other sharers. The previous sharer of the data will acknowledge that. Similarly, this requester will invalidate the copy in the home node. Home node will acknowledge, and write to Z can now proceed. Okay. Now in the next few slides, we're going to switch slightly on the direction. We're going to look at memory consistency issue. Let's look at this example. We have two processors, and in their shared memory, there are two variables A and B, both at 0 at the beginning. The code on processor 1 is assign 1 to A and assign 1 to flag. And on processor 2, the code is it's going to block when flag is 0. When flag becomes not 0, it will proceed to the next line, which is print A. The question is it possible that P2 prints A equals 0? Let's see. If the initial flag is 0, it's not, right? Okay. Second example. Still two processors. On processor 1, we have two assignments. We give value 1 to A and then to B. On processor 2, we print the value of B and then print the value of A. Question is it possible P2 prints A equals 0 and B equals 1? No, right? Okay. So because when you write the program like this, you have that sequential logic that you have an assumption that the orders of these loads and stores will be exactly as you have in the program. Okay. So the programmers anticipate certain memory ordering and program behavior. But this becomes very complex when you have shared memory programs, and also when you have processors that may execute instructions out of order. So the memory consistency model we're talking about here specifies the legal ordering of memory events when several processors access the shared memory locations. That's the topic we're discussing here. There can be different memory consistent models, as you will see, but the very common one is the sequential consistency. What is sequential consistency? The definition is here. A multiprocessor is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in the same sequential order, and the operations of each individual processor appear in the sequence in an order specified by its program. And that's very strict. So whatever statements you have in your program, that order has to be followed strictly in sequence. It has two properties. One is the program ordering, which means that whatever you have in your program, that order is what the processor should follow. This other property is the write atomicity. This is particularly important in the multi-core environment. So this atomicity of write operation is to say that all the writes to any locations should appear to all the processors in the same time. So if one processor writes to a location, before this is seen by all other processors, it should not proceed. That's essentially what this implies. That's how you can ensure this atomicity. If the writer processor, the processor that initiates the write, continue the operation without waiting for other processors to see this, that violates the atomicity, then it's not in the sequential order. Sequential consistency model. People have been writing programs on uniprocessors for a long time. This problem is not there. This consistency problem is not there when you have a uniprocessor programming environment. This becomes a problem when you have multi-core processors or multiprocessors. Because this sequential consistency requirement, there are some performance penalty because the other processors cannot move forward until this write operation is completed, is propagated to all other processors. So to illustrate that, you essentially have this kind of like a time pointer that you have to go through every processor that before you can advance to the next tick. Here's a sequential consistency example. We have 4 processors, okay? P0, P1, P2, P3. And vertically from top to down, we assume that's how time progresses. And at the beginning, we have 2 updates to data. We have P0 assigning 1 to A, and P3 assigning 2 to A. And then we have P2 assign A to Y, and P1 assign A to T. And at some point later, we have P1 assign A to U, and P2 assign A to Z. So what we expect to see in a sequential consistency model is this. Okay? It's one possibility. This is the case when we execute this, we propagate it, and then we execute these 2, and then we execute this A2. Yeah. Not exactly the same time because we don't have a time slot that indicating this. This figure is trying to illustrate what are the operations that's programmed on these processors. It does not mean that these 2 statements will be executed at the same time. It's a little bit confusion here, but this is what this figure is trying to illustrate. If this machine follows the sequentially consistent memory model, we will probably have something like this. Or the other way around, we can we may have T1 equals 2, Y equals 2, U equals 1, Z equals 1. That's also possible. Because the requirement is that this write autonomously, right? When you write, this write has to be seen by all the other processes. Now we do this. If we use a different memory consistency model, we may have something like this as the result. Okay? It may happen that the write to this A, this write is done by either P0 or P3, depending on how soon these other two processors see these values. You may end up having this. So T1 is 1 because it may see this A first update by P0 first, and this update second. So that's why you see these two values. Whereas on P2, you may see this update first and then this update, if there's no write autonomously. This is a violation of the sequential consistency. But as it says here, it's possible in processor consistency model. It's different from the sequential consistency. Okay, let's look at this example. This is actually the famous Decker's algorithm to implement critical section. The exact algorithm is a little bit more complicated than what's illustrated here, but the main principle is the same. What this algorithm does is two processors, it tries to implement mutual exclusion. Assume there's a critical section that only one of the processors may enter. So this is the algorithm you may use. Assume that these flags 1, 2 are both zeros at the beginning. It'll check on P1. Well, it first assign 1 to flag 1 and check if flag 2 is 0, then it'll enter. So whoever gets entered, it'll make sure that my flag is 1, the other person's flag is 0. That's what this is about. But this works fine on a uniprocessor environment, but it violates the ordering on a multiprocessor environment. What we're seeing here is two processors with write buffer. Okay. P0 writes to flag 1. And for P0, it sees flag 2 is still 0 because of the write buffer. Suppose it's a writeback cache. And similarly, P1 will see its own flag is 1 and the other flag is 0. So as a result, both of them will go into the critical section. So that's an issue. Atomic and instantaneous update. The update of a variable must take place automatically to all processors. In this example, we have two variables, A and B, both at 0 at the beginning. We have three processors. Each processor have a different program to run. First processor update 1, and the second processor will check if A is 1. If that's the case, it will update B. And similarly, P3 will check B. If B is 0, it will update R1 with the value of A. A read cannot return the value of another processor's write until the write is made visible by all the processors. That's what we really want. But if an update is not automatic to all, in the earlier example we saw that if we have these processors connected in series, this linear connection will cause the propagation delays. So for example here, if we have update to A1 coming from P1, okay, so this P2 updates B1, and by the time it reaches P3, P3 does not have the update of A value. So in this case, it will cause an incorrect program result. So R1 will get a 0 rather than 1. We've seen that caches, especially write-back caches, make things complicated. A P3 may caches A and B. So A1 will not show up in P3 until P3 reads it when it operates the R1 updating with the value of A. Compared to the sequentially consistency model, there are other models, so-called relaxed memory models. We can relax order in the following ways. We can allow load bypass a store. We can allow load bypass a load, store bypass a load, store, or store bypass a load. And we can also relax write automaticity requirement, either by read others write early or read own write early. Now keep in mind that by relaxing the memory model, you cannot, when you look at the first two simple programs, you cannot just assume what will or will not happen. Because if the sequentially consistent model is not there, then anything could happen. So in that case, you have to, as a programmer, use, for example, memory barriers or other synchronization primitives to control the program to maintain the correctness of the program. So the processor, when you allow this relaxed memory model, they will run faster because, for example, they do not have to wait until all the write automatically to complete. So this relaxed memory model is for the purpose of improved performance, but it adds requirement for the programmers. Programmers, you cannot assume that this load will precede that store. You have to use additional statements in your program to ensure the correctness. We talk about one example here, the processor consistency. This is used in Intel's P6 architecture, which is Pentium Pro. The write visibility could be in different orders of different processors. There's no guarantee write autonomously. It allows loads to bypass independent stores in each individual processor. So to achieve this sequentially coherent, you have to use explicit synchronization operations in your program. You can do read, modify, write instructions, or using memory barrier or memory fence instructions. Let's just look at this one example. So we have two programs, two processors. This is to assign 1 and 1 to F1A, and then we'll assign the value of A to R1. And the last statement of this program is to do assignment. We're going to assign the value of F2 to R2. Okay. And on the other one, we assign 1 to F2, 2 to A, and A to R3. We'll assign the value of F1 to R4. Okay. Assuming all the initial values of these variables are 0. Okay. If we allow load bypassing stores, when we look at this first example, these are stores. Okay? These are all stores. For this very last statement, we actually load F2. Okay? And because this F2 in this program, there's no dependency, right? There's no dependency on the F2 in this first program. So if we allow this, have this kind of processor consistency model, we actually can allow loading of F2 happen ahead of time. And similarly, we can allow this loading of F1 happen ahead of time because it's not a dependent variable. As a result, you may end up having this as the outcome. R1 is 1, R3 is a 1, and R2 and R4 are zeros, because this 0 is due to the early loading of F2 and early loading of F1. In this consistent model, we have these programs on P1, P2. A is 1, flag is 1. On P2, we check this flag. We wait until flag is not a 0. Okay. So this is intuitive for event synchronization. So A must be printed as 1. Back to the Decker's algorithm. If you use this flag 1 and flag 2 to decide when a processor can go to in critical section, because of the relaxed memory model, we can allow load bypassing store. So actually, both of them may end up going into the critical section. So there's no guarantee this mutual exclusion. In the very last example, you've seen before, P1 has assignment 1 to A, and P2 check A, assign B, and P3 check B, assign R1. And in this case, this load of A could happen early, so R1 is 0 as a possible outcome. Okay.
the logic of the function that we
So this is to say that if you do not have any synchronization primitives or memory fence primitives, when you write a program like this, running on a processor with this kind of processor consistent model, you may end up having a program outcome which is different from you expect. Because oftentimes you assume processors are designed that supports the strict sequentially coherent model, but it may not be the case. So when you write your program, you have to consider when do you do locks, when do you wait, when do you do a memory fence so that everyone gonna synchronize at that point. Well, what's the trade-off? You are making your program more complicated, right? For the sake of better performance. Because your program or other people's program may not need that sequentially coherent model. You may not need to wait the write being committed automatically. That's the idea.